Hello everyone. In this lecture, we will mainly talk about the partition of positive integers. But before that, I will give you another application of the generating function we learned in the last lecture. So here is a theorem. So let Hn be the number of ways of dividing a convex polygonal region with n+1 sides into triangular regions by inserting diagonals that do not intersect in the interior. And since we don't have a polygonal region with two sides, so we need to define artificially, manually, h1 is 1. So the first conclusion is we have a nonlinear recurrence relation as follows. Hn is h1 times hm minus 1 plus h2 times hm minus 2 plus all the way to hm minus 1 times h1. Or if you like, we can also write it in the following concise form: hk times hm minus k for all n greater than or equal to 2. And secondly, based on this recurrence relation, we can further derive the actual formula 1 over n, 2n minus 2, n minus 1. Before we give a proof, I first would like to say this is called the Catalan number. But actually, the usual definition for the Catalan number, you need to shift to 1 a little bit. That is, Catalan number Cn actually is hm plus 1, which is 1 over n plus 1 times 2n choose n. So this is a Catalan number. Okay. So also, I would like to discuss what is a procedure of dividing carefully by examples. So suppose you have a hexagon, and now so you can divide the hexagon into 4 triangles in this way or in some other ways, depending how you connecting the diagonals. Noted that we require the diagonals don't intersect in the interior, so you will have this kind of thing, and you will have finitely many ways to do that. So Hn is actually the number of ways of dividing the hexagon. So here H5 ways dividing the hexagons. Okay, now let's look at the proof. So for H2, we know that this is a triangle, so you don't need to do any cutting anymore. So therefore, H2 is 1. And for H3, noted that for the square or the rectangle, you can connecting the diagonal with a positive slope all connecting the diagonal with a negative slope. Therefore, basically you have 2. You can do this way to enumerate HM for the small numbers, but then for the larger number, you do need to have some other argument, either by induction or whatever. So for n greater than or equal to 4, then our method is fix aside T of the polygonal region R. So we have many sides. I don't care. So I first fix one side. I call it T. So this is a T. And the whole region is called R. Okay. And based on T, we can take the triangle T hat containing T. Yeah, you might have many choice. For example, you connect two endpoints of T with another vertex of the polygonal region. Okay, and this will be your T hat. Okay, and after that, you notice that actually you divide the whole region R into 3 parts. One is T hat, and on the left side of T hat you have R1, on the right side you have R2. Okay, then the region is divided into 3 parts, R1, T hat, R2. Okay, then we can compute so the number of ways of dividing or such dividing or such division equals. So here such means you have T hat T hat is as above. Is equals number of ways dividing R1 times the number of ways of dividing R2. Okay, here if we want to discuss the right-hand side, we'd better to give more information for R1 and R2. For example, here R1, we can assume it's a polygon with k plus 1 sides, and then the right-hand side will be polygon with n minus k plus 1 sides. Okay, therefore here, the right-hand side can be further by induction. The first term is hk, and then the second term is hm minus k. Okay, noted that T hat runs over all the vertices of R, the whole thing R. and then we have Hn equals summation for k from 1 to n minus 1 hk times hm minus k. We don't have h0. K cannot be taken as 0 or m because otherwise the term is one of the factor is 0. Okay, so this is the first part, and then for the second part, we consider the generating function. And notice that for the generating function, we consider this one. Not exactly starting from 1, but instead we're starting from h1 times x, the second, the linear term. And then gx squared. What is gx squared? This is h1 squared x squared plus h1, sorry. Oh yeah, that's true. And then you have h1 times h2 plus h2 times h1 x cubed plus h1 h3 plus h2 h2 plus h3 h1 x2 fourth and plus h1 h4 plus h2 h3 plus h3 h2 plus h4 h1 x2 fifths. And then by the recurrence relation, we know this is h2x squared plus h3x cubed plus h4x fourth. So this will be gx minus h1x. Since h1 is 1, so you have gx minus x. Okay, although you don't know what is g, but you do have a quadratic equation. And to solve it, you have two solutions. But notice that when x is 0, g should be 0. Then the first solution isn't it the one we want? So gx should be the second one. But this is good, but if we want hn instead of the whole generating function, we still need to work a little bit. And to do that, we recall a formula that is fraction Newton's rule. So how to expand this into an infinite series? I don't know if you learned the Taylor expansion, but if you don't, just search online. It's quite easy. Just take a derivative and use the derivative as your coefficient. So basically, you will have this one. Even I didn't tell you what is the actual rule, but you can find the pattern. Plus, and for the nth term will be -1 to n minus 1's power, 2 to n's power, 1 times 3 times 5, all the way to 2n minus 3 divided by n factorial, z to n's power divided by n factorial. Okay, and we simplify. Let's simplify the generic term. So the generic term is -1 to n minus 1's power 2 times n. And since we don't know how to do 1 times 3 times 5, but we do know how to do multiplication from 1 to 3, 4, all the way to 2n minus 2. Then if you do in the above, in the bottom, you need to divide the actual 2 times 4 times 6 all the way to 2n minus 2. And if you figure out 2, this is negative 1n minus 1 to n minus 2 factorial n factorial 1 over 2 to n minus 1's power times 1 times 2 times 3 times all the way to n minus 1. Okay, and you simplify it, you will have this is 2n minus 1 2n minus 2 factorial n minus 1 factorial. Okay, and if you want a combinatorial number, so let's change it a little bit. You have this, and then this will give you 2n minus 2, choose n minus 1, 1 over n. Okay, now look at the function g. So gx is 1/2 minus 1/2, 1 minus 4x, 1/2. If you use the above formula, so inside you will have 1 minus summation 2 over n, and from 1 to infinity, 2n minus 2, n minus 1, x to n's power times yeah, that's it. So here you need to do a little bit of computation. I omitted it. So why? Leave it to you. You just plug in the formula. Okay, and then from this, we know that so Hn is 1 over n to n minus 2. Choose n minus 1 for all n greater than or equal to 2. But if you look at H1 case, and this is also true, therefore the formula is general. Okay, so this is Cartesian number. You can see actually the way we can use a generating function is very general. So sometimes it's outside of our imagination. Okay, next we will talk about a very interesting topic. It's called partition of positive integer. N is our representation of n as an unordered sum of positive integers, which we call each one is called a part. So as a generally we call them parts. So 1 can be only written as summation of 1. And for 2, you have 2 partitions. First is 2, second one is 1 plus 1. So in the second partition, 1 and 1 are parts of the second partition. So 3 is 3, or 2 plus 1, or 1 plus 1 plus 1. 4 is 4. 3 plus 1 equals 2 plus 2 equals 2 plus 1 plus 1. Or equals 1 plus 1 plus 1 plus 1. Okay, you can also enumerate all the partitions of 5 by yourself. And in some textbook, they would like to write a partition as lambda n to a(n's power times n minus 1 to a(n minus 1's power, and 2 to a2's power times a1 to a1's power. But don't, so this is a remark, don't misunderstand this as a product. It's not. If it's a partition, if you see some textbook do this, and by the above or the following context, you should understand this as a partition or more explicit. It should be n plus all the way to n piece, and n minus 1 plus n minus 1 n minus 1 piece plus 2 plus all the way to 2 a2 piece plus 1 plus all the way to 1 a1 piece. Okay, and this is how we understand this problem, but you can also understand this problem or formulate the problem in the following rigorous way. So Pn, let's define Pn to be the number of ways of partitions. The number of partitions of n, or you can formulate as Pn is the number of integral solutions of n plus n minus 1 n minus 1 plus all the way to 2a2 plus a1 equals n, and each ai is non-negative. So previous, when we discuss permutation or combination, we use this this form, just like counting the integral solutions of certain indefinite linear equations. So here the only difference is you change the coefficients of variables. And similarly, you can also ask, define some special partitions, like partition an even number into several parts, such that each part is also even number. So in that case, you should change the coefficient to even numbers, 2n minus 2, 2n minus 4, all the way to 2. Or you can do whatever you want according to your expectation. Okay. This is also true in mathematics. For the definition, you can always do all kinds of weird things, but from the reality, the most interesting one, probably just the most natural one. Okay, and next we are going to define what is called the Ferrodi diagram. This is very important, and it's closely related to the Young diagram in the algebra, in physics, in computer science. I don't know if it's in statistics, but if it is, I won't be surprised. Okay, let lambda be the partition, n equals n plus 1 plus n1 plus n2 plus all the way to nk, where n1 is greater than or equal to n2. So you have a decreasing sequence. And then the Ferrodi diagram of lambda is left justified array of dots that has k rows with ni dots in row in ith row. So let's look at one example. Probably one example is good enough to illustrate everything. Suppose you have 10 equals 4 plus 2 plus 2 plus 1 plus 1, and then the first row, you put 4 dots, and then second row you put 2 dots, such that the first dot they are in the same column, and then second one is 2, the fourth one is 1, last one is 1. So how do we decide the number of dots in each row? So suppose this is N1, and first you arrange all the parts in your partition in the decreasing order, just like this one. And then the first number in the first part in the partition corresponding to the number of dots in the first row, and the second one goes to second row, third one goes to third one. So this is how we draw the Ferrodi diagram, and it's easy to see. Give a partition is equivalent to give a Ferrodi diagram. Okay, and before we going on, I would like to see, actually we can also define order on all partitions. So first, we would like to define the partial order. So let P be the set of all partitions of N greater than or equal to 1. Actually here you can this is a more general way. That is, the number N can also change. Okay. So define a natural partial order Chi P as follows. So for convenience, we make the following notation, make the following convention notationally: include 0 as parts. So this is special when we define the order, because it's more convenient when you compare different partitions with different number of parts. Otherwise, it's tedious. You need to say, okay, if you have 0 parts, whatever. But this is, I just want to say this is just for technical reason. Make the following convention. It's not necessary. If you don't like it, you can use a little bit more tedious way to state the result. Okay, suppose you have 2 partitions of N, and also arrange them in the decreasing order. If they have different lengths, then you just add zeros for the shorter one, so that they have the same length. Length means the number of parts. Okay, and then lambda is called less than or equal to mu if and only if n1 plus n2 all the way to ni is less than or equal to m1 plus m2 plus all the way to mi. So for all I between 1 and k. So if you don't like this notation, you can write down all the inequalities as a definition. n1 plus n2 less than or equal to m1 plus m2, n1 plus n2 plus n3 less than or equal to m1 plus m2 plus m3, and finally n1 plus n2 plus all the way to n k less than or equal to m. Sorry. In this case, or from the definition, this is also gives you this, and I would like to make a remark. If lambda and the mu are partitions On, then the last one must be the equality instead of the inequality. But we would like to define in this form because this definition can extend to partitions or different numbers. In other words, lambda can be partition of capital N, n1 plus n2 plus blah blah, and the mu can be a partition of capital M. So N, capital M can be different. You can also run this definition. Of course, not every two partitions can be compared, but they do give you some natural partition. Okay, now let's look at several examples. So first, we introduce three partitions. First is partitions 9. 5 plus 1 plus 1 plus 1 plus 1. Mu is 4 plus 2 plus 2 plus 1. Nu is 4 plus 4 plus 1. And then for the first term, we have 4 less than or equal to 4 less than or equal to 5. But then for the partial sum of the first two terms, you still have 4 plus 2 less than or equal to 4 plus 4. But 4 plus 2 is 5 plus 1. So for the partial sum of mu and lambda, they are same, but nu bigger than mu and lambda. Therefore here, you already know that mu and lambda are incomparable. Okay, next, so we need to consider, so here actually totally you have three pairs, nu, mu, nu, mu, lambda, nu, lambda, and then by discussion, we don't need to consider nu lambda anymore, they are incomparable. And for mu and nu, let's consider the partial sum of first three terms. You still have this one, but then 4 plus 2 plus 2 greater than 5 plus 1 plus 1. So this means mu and the lambda are incomparable. Okay. So let's verify the summation of the first four items, but then since you know this is already 9, so it's always greater than the partial sums. Okay, therefore we finally conclude that mu is actually less than or equal to nu. So from this example, you can also see that we do have a partial sum. Okay, and then a natural question is, can we extend the above partial order into a total order as follows. So actually this order, just what we learned before, it's lexicographic order. So suppose you have 2 partitions arranged in the decreasing order. And then lambda less than or equal to nu, or sometimes in the lexicographic order, we would like to say lambda precedes mu if and only if exists I such that nj equals mj for j less than I and ni less than mi. Or you can understand this way. So they tied at the very beginning, and then suddenly one partition leads the other one. Then you just forget about the remaining items. This leading keeps to the final order. Okay, next we would like to discuss one of the interesting aspects of the partition. So we have a lot of partition identities appear either in physics, string series, particle physics, condensed matter series, number series, all kinds of research fields, also in computer science. And probably the most famous masters in this area will be Euler and Gauss and Ramanujan and Hardy, Littlewood, whatever. Actually, Hardy and Littlewood are just give rigorous proof for Ramanujan's work. And if you want, I believe this will be a good topic for some reading report. You can find some nice partition identity paper and then introduce them, learn something from there. Okay, and before we talk about very deep identities, we would like to first show that for some restricted partitions, you already have some identities. So let n and r be positive integers with r less than or equal to n, and let p and r be the number of partitions or n in which the largest part is R, and let Q and R be the number of partitions of M minus R in which no part is greater than R. Then we have P and R equals Q and R. So this is the number of some partitions and more restrictive conditions. This is another type, the number of partitions and another type of restrictive conditions. So actually the proof is quite easy. So let's denote T to be the set of all such partitions in the first sense, and then as a set of all such partitions, S is a set of all such partitions, and the second restrictive conditions. Okay, now what we are going to do is construct a correspondence between the partitions in the first set and the partitions in the second set. So actually this is quite easy in this problem. So just whenever you are given a partition in the first set, removing a part equal to R, or you just delete N1. So more precisely, suppose lambda is N1 plus N2 plus all the way to Nk, and N1 is greater than or equal to N2, greater or equal to Nk, and define lambda prime equals to N2 plus N3 plus all the way to Nk. So this gives you a partition in set S. Okay, and similarly, you can construct an inverse map by inserting a part equal to R. Then it's easy to verify that this is one-by-one correspondence. Therefore, the cardinality of these two sets are the same. So we are done. Okay, and so another identity I'm going to show you is due to Euler. So let Pn0 be the number of partitions of n into order parts. So here I would like to explain a little bit more. Order part means each part is odd. Okay, and then Pnd to be the number of partitions of n into distinct parts. So in other words, n1 greater than n2 greater than n3, there's no identity between these inequalities. And let's call the first one, define this set to be all such partitions in the first restrictive condition. And then for the second one, let's call it D, all such partitions. Okay, then Ola claimed that Pno equals P and D. And the idea will be similar. We are going to construct a bijection between these two sets. So first we would like to construct the map, which give each element in O an element in D. And suppose lambda is given by n1 plus n2 plus all the way to nl. And noted that there might be identities between these parts. Okay, if ni equals nj for certain I different from j, let lambda 1 be the partition defined as follows, defined by you still have n1 all the way to nl, but so this sign means head means deleting. You don't have this anymore. Okay. But you still have the next term, the term after it or the term before it. And then you also delete nj. You noted that if you do this, actually you are missing some part of the identity. It's not an identity anymore. For it to be still an identity, you need to put an extra term, so that will be 2ni. So let's use this extra. So these two are deleted. Okay, and then repeat the above procedure. Therefore, for lambda, you have lambda 1, and then you have lambda 2 all the way to. Notice that this procedure will not repeat forever, because each time the length is decreased by 1. So first, for lambda, you have k turns. For lambda 1, you only have k minus 1 turns. So you are decreasing the length, because the length is always positive. So it cannot repeat forever. And then the last one, let's define lambda prime to be the last, to be the resulting partition in the last step. Okay, of course, here you have a bigger issue, that is, show that lambda prime is independent of the intermediate steps, because in a partition lambda, you might have a lot of pairs or repetition, and each time you can only choose one pair. So for different choices, you might have different intermediate steps. But to construct a well-defined map, you do need to verify that the final result, lambda prime, is independent of the intermediate steps. Okay, and suppose this is done, so I leave it to you. Next, we are going to show the inverse direction. That is, for each partition in D, we construct a partition in lambda. So suppose lambda prime is n1 star plus blah blah plus all the way to m star. Okay, and here you do have you can assume the decreasing property. Okay, if n1 star all the way to nm star, are odd, let lambda just be lambda prime. Because we're done, it's already an element in O. Otherwise, let ni1 star, ni2 star, ni lambda star be the even parts. Even parts means those numbers are even. And then define lambda 1 prime by n equals n1 star plus ni1 star. You delete this and delete all the here you have prime. I lambda prime just means this index is depending on the partition. You get rid of this, and just as before, we do need to add some extra terms. So here, how to add extra terms? You just divide each even part by 2. Okay, and here, see, delete, and those are extra terms. Okay, and after this step, probably you can get more odd part or deleting more even parts, but probably you still don't have an element in capital O. So what you are doing is from lambda prime, you have lambda prime 1, lambda prime 2, and all the way down. And then the important thing is you don't want this step continue forever. This procedure continues forever. So you need to have some invariance to control the sequence. This is a crucial part, I think, in many important mathematical theorems. You do have some procedure, but you also do want them to terminate at some step. But it will not terminate just for free. You need to have some elegant invariance to control it. Recall in the first construction, we use a length to control it. And in the second step, we also use the length, but now the length is increased at least by 1 each step. But also the largest length of a partition of n is n, because you have n equals 1 plus 1 plus all the way to 1. So you cannot have more items. So that tells you it will terminate at finite step. Okay. And define lambda to be the final result. Okay, and then you can verify this is a bijection. And actually here I should say you do have more. That is, suppose this is L1, this is L2, remark. L1 compose L2 equals L2, sorry, is the identity map. So lambda maps to lambda prime, and the lambda prime maps to lambda. So you have involution. Okay, and before we proceed, I would like to introduce our general way of, so this is called involution, very important, involution. And next, I'm going to define another very important involution among the partitions, that is called conjugate partitions. Lambda O n is sorry. I should say like this. A conjugate partition of lambda of the partition, sorry about that. Lambda O n is a partition lambda star whose diagram is obtained. So here diagram means Ferrodi's diagram. Obtained from the diagram of lambda by interchange rows with columns. Another way to view this is flipping over the diagram. Sorry, flipping over the diagram over the diagonal, running from up left to the lower right. Or the diagonal with negative slope. So remark or example. So suppose you have suppose you have, 10 equals 4 plus 2 plus 2 plus 1 plus 1. This is your lambda. This is your lambda. And what is the lambda star? You do need to flip, or so flip will be along this diagonal. Okay, or you change the row and columns. So you will have, let's see, 4, 2, 2, 1, 1. So more precisely, this first row becomes first column, and second row becomes the second column. Third row becomes the third column. And the extra similarly. And then you will see lambda star. So it's 10 equals 5 plus 3 plus 1 plus 1. Of course, you do have a mathematical way to define it. Suppose lambda is given by n1 plus n2 all the way to nk, and you can define lambda star by n1 star plus n2 star plus nl star. So here, where L is n1, L is n1, and ni star is cardinality of the set J of J such that nj is greater than or equal to I. So for I between 1 and L. This is a mathematical way to define it, although it's pretty precise, but it's hard to imagine, and actual computation for lower ranks is not that easy. And then you do have some special examples that they call self-conjugate partition. That is the case when lambda is lambda star. And a very interesting property is if you do conjugate twice, you always get back to the original partition because you flip over the diagonal twice, you just give back the original result. Therefore, the conjugate is an evolution. Okay. So next we are going to discuss another type of identities. So PNS is a number of self-conjugate partitions ON, and PNT is a number of partitions ON into distinct order parts. Order parts means each part is ordered. And then these two numbers are the same. And I would like to call the partitions in, and the first condition, element of set S and the element of set T in the second case, and how to construct the bijection map. So first we construct the map from S to T. So suppose lambda is given by n1, n2, nl, and then you define. First, I will give you some geometrical intuition. So self-conjugate means it's symmetric along the diagonal. Therefore, we can do the following procedure. We look at the first row and the first column and counting the total dots in those positions. And then we count for the remaining part. We also do the similar procedure. Okay, suppose let's give it one more. Okay. And then you're counting it, so the number of dots, let's call it n1 star. And then here, let's define n2 star be the number of dots in those positions, and then n3 star number of dots. Or mathematical, then you define lambda star by n1 star plus n2 star plus all the way to nm star, and or mathematically or more rigorously, let's define n1 star be 2n1 plus 1, n2 star be 2n2 minus 1, n3 star be 2n3 minus 3. So nk star be 2nk minus 2k minus 3. And finally, you will have nm star is 1. So notice that n1 is greater than or equal to n2. So you do have n1 star greater than n2 star strictly. And also, it's easy to verify that the summation is n. This is by the property of self-conjugate partitions. Okay, and similarly, you can reverse this procedure. Or we can construct just a map from from T to S. Okay. So let's see. Next, we are going to talk about the very important Euler's pentagon number identity. So first, recall that we have the following theorem. So the generating function for the number of partitions actually is the product of 1 minus xk's power to minus 1's power. So proof is easy because right hand side equals 1 plus x to 1 times a1's power. times 1 plus x squared plus all the way to 2 times a2's power, and times 1 plus x cubed, blah blah, plus x3 times a3 plus. And if you sum them up, you do the distribution law, this is exactly left-hand side. And Euler's starting point is so next we're going to talk about this. Starting point is he noted that, so recall that right hand side, so this is star, right side is 1 over product 1 minus x to k's power, k from 1 to infinity. And although the generating function is very hard, but then the inverse of the generating function or reciprocal of the generating function of Pn is easy. This is a very non-trivial observation because you do have a lot of cancellation. So what is the result? This is very, very non-trivial, and probably at least at his time, not a lot of people think about this. This gives you a very sparse sequence, and also the coefficients is either 1 or -1. So it's 1 minus x squared plus x fifths plus x sevenths minus x 12 minus x 15 plus x 22 plus x 26. Okay, or you can organize them in the following two ways. So firstly, you can organize it as summation -1 to k's power x k times 3k plus 1 divided by 2 plus x k times 3k minus 1 divided by 2. Because here you do have twins for each summation, for each for certain adjacent two elements. Or if you don't like this formula, because you do have different formula, so you can write in the following way. If you admit negative parameter k. Okay, and so let's call it gk be the generalized pentagonal numbers for k equals 1, -1, 2, -2, blah blah. And the easy corollary is Pn is summation of all -1k, all k different from 0, -1k minus 1 times Pm minus gk. Gk is a pentagonal number, and prove. So this, we prove this based on the so we haven't proved this, but we are going to prove at the end. So based on the Euler's pentagonal number theory, it's quite easy because 1 equals the generating function of Pn times 1 minus x to k's power for all k. And then if you expand it by the Pentagon theorem. So first one is by definition. First identity is by definition. Second one is Pentagon theory. -1 to k's power xk 3k minus 1 over 2 plus xk 3k plus minus, here's plus, over 2. Okay, and if you look at coefficients of xn, you notice that now here you should have 1 plus and starting from 1. Yes, this is true. Okay, and you will have on the left hand side is 0. So right hand side is Pm plus -1 Pm minus G1 plus Pm minus G -1 and the plus -1 square P M minus G1 plus Pm minus G -1 Pm minus G2 plus Pm minus G -2 and blah blah. Okay, and since Pm grows quadratically, Gm grows quadratically, so this summation is finite. Okay, next we are going to prove star. But very briefly, if you have interest, you can work out the details. So first, note that left-hand side of star can be interpreted as 1 plus n from 1 to infinity Pem minus Pon xn. So what is Pen? This is the number of partitions whose number of parts is even. In other words, the length is even, and this is the number of partitions whose number of parts is odd. Oh, sorry. Whose? So I omit one condition. Partition with distinct parts, and the number of parts is even. And here, similarly, this is with distinct parts, and the number of parts is odd. So I leave it to you, verify it. Okay, then we can construct, so next we will explain how we have cancellations. How cancellation are possible. So let lambda be a partition. Be a partition with distinct parts. And here also assume the decreasing order. And let S, so S is a very important invariant. Let S be the largest integer such that n1 is ns plus s minus 1. In other words, we have n1 is n1, n2 is n1 minus 1, n3 is n2 minus 2, ns is ns minus s plus 1, but ns plus 1 is strictly less than ns, here is n1. This is n1. n1 minus s. So this s is an invariant we are going to use. And now, if s strictly less than nl, define lambda prime be a partition. N1 minus 1 plus N2 minus 1 plus NS minus 1 plus NS plus 1 plus NS plus 2. Notice that we are missing one term. We are missing something. So finally, you should give an actual. So this is an actual. And if NL less than or equal to S, define lambda prime to be a partition. So here, now each one is increased. Okay, and so here is NL. Let's think about yes. So L plus 1, and then NL plus 1 plus blah blah blah, and until the last one, the one before last one, so there will be NL minus 1 and plus yes, this will be the last one. So if I write is, this one is cancelled, delete. Or if you, it's better to use the previous notation. Delete. Okay, then noted that. So here the crucial thing is, noted that lambda maps to lambda prime, and then lambda prime, this is gives bijection map between, so let's call here this set E, this set E, this set O. This be a bijection between E and O. If this is true, then the Euler's pentagon theorem is wrong, because you do have some extra terms, and then except the following cases. So that's why this is a really interesting theorem, which is different from previous theorem, which states this number exactly equal that number. Those are trivial, actually, except the following cases. This you do need to have some genius. Okay, except when S equal NL and so let's see. And here, so the last condition is a little bit involved, but I would like to try my best to state it clear. So, and L equals here I should say L equals NS equals NL. So you will have, this suffices. So this part is just a geometric picture. So you will have this shape, and counting the dots, that gives you k times 2k minus 1, 3k minus 1 divided by 2. And all the other case is L equals NL equals S minus 1. So this corresponds to dot for just like this shape. And if you compute the total dots, is k times 3k plus 1 divided by 2. Okay, so for each n equals those two numbers, pentagonal numbers, you only have one case, one partition, which either gives you no corresponding maps in the different set, or just a map to itself. So that's why you have one negative one in that case, and blah blah. You can complete the proof, but the main idea is here. Okay, I will stop here. And yeah, I know this week's video is a little bit longer than usual. If you're not able to complete everything, you can choose a material you'd like, especially for the Euler's pentagonal number theory. If you don't like it, you can skip it. But I would strongly recommend it to you.